Oh, and your homework at any time during the lecture, if you read my email yesterday night, you can drop off your homework in that box over there. All right, so the last thing that we had come up with was an expression for what we called an elementary rate law. We said if there is some consumption of a species, we have a way to at least get started with these problems by assuming that the reaction is what we call elementary. And we saw that the general form for that A plus B goes to C plus D form was minus R sub A is equal to some coefficient lowercase k times the concentrations of your reactants raised to whatever their stoichiometric coefficients are, A and B. Remember, this was generally for AA plus BB goes to CC plus DD. Normally, we don't get quite so lucky that things are what we call irreversible, that they just go from reactants to products. There are a few reactions that are like that. In fact, one that's causing everybody a lot of problem right now is combustion. Right? Combustion is primarily a one-directional process. You start with fuel and you end up with carbon dioxide. If that were a more reversible reaction, we could do something about that CO2 and get it to go back to fuel, but that's pretty hard to do. What's really good at taking CO2 and essentially turning it into fuel? Yes, catalyst, but in a particular application. I think somebody else said it over here. Photosynthesis, plants. They can take it the other direction. We are not very good at it. We know the kinetics to do it, we just can't do it on a large scale. So there are a handful of reactions that are, for the most part, irreversible. Once you react, whatever your reactants are, you're stuck with the products and they never go backwards. Most reactions that we deal with are not irreversible. They are what we would call reversible reactions. And so to denote a reversible reaction, we get rid of the one-way arrow and we add the two-way arrow. That is a reversible reaction. If that reaction is elementary, we can still write an elementary rate law. It's just that now we have essentially two directions that this is going. So now instead of just R sub A, I'm going to put a line through that because this was for a irreversible reaction. Now we have this. R sub A is equal to, starts out the same, K C sub A, C sub B, raised to their stoichiometric coefficients. But this is what we would call the forward rate law, right? If forward meaning if we really go from reactants to products in the way that it's written in our equation, this is what a forward rate law would look like. And so we subscript the K with a little lowercase f to stand for forwards. Right? This is what happens if we go from left to right. Then we can write another one, K times C sub C and C sub D raised to their stoichiometric coefficients. Except now instead of the forward reaction, we have a reverse reaction or a backwards reaction. Depending on what book you see, some people will say K sub B for backwards or K sub R for reverse. We actually don't use lowercase k in this way very often, so I'm just going to call it K sub B. And intuitively, what do you think the sign should be in front of that? Should we add it or subtract it?
Subtract it.
Probably subtract it, right? If the forwards rate is talking about how much we're consuming our reactants, the backwards rate is how much we're producing those same reactants because we did something with our products. So this ends up getting a negative sign here. So we can write a reverse reaction rate for the reverse elementary reaction in exactly the same way we did for the forwards. It just has a different rate constant K associated with it. The reason that I said we don't use K sub F and K sub B very often is because we have another K that we use, which is the capital K. The more common form, and about the only form that we're going to use in this class, is K forward times CACB, oh, that one was supposed to be capital A. And then we essentially factor out that K sub B and replace it with another K. So we have CC and CD here raised to their powers over the first capital K that we're going to deal with, which is Kc. So in this particular equation, the way we've written Kc here, it has been defined in a particular way as K forwards over K backwards. So capital Kc is rate constant K forwards over rate constant K backwards. This Kc is called the equilibrium constant in terms of concentration. And when I say concentration, I mean concentration C. I am going to define an awful lot of these Kc's. Each one has a different interpretation based on how that Kc is defined, and the notation to distinguish between those K's is to put a different subscript on it. So when you see K sub C, that's the forward rate constant over the backwards rate constant. The reason that it's called K sub C, there are no C's in the way that we've drawn it right there, is because the more useful definition that we use is that Kc, this is one of those mouthful of things that is easier to write down once you see the pattern than to say it. It's the product of the concentrations of the products raised to their stoichiometric coefficients divided by the product of the concentrations of the reactants raised to their stoichiometric coefficients. So this would look something like C sub C raised to the C, C sub D raised to the D, over C sub A raised to A, and C sub B raised to B. The shorthand notation for that is the equation that you saw on the first slide, which is the product of all of the concentrations I raised to their stoichiometric coefficients. This is why we call it K sub C. Let me put those caps on there just so that you remember that this is K sub C. This is where we get that C from. It's the product of all of the concentrations. The one in blue is the one that we use more often. There's nothing wrong with using the one in red. It's just we don't use it that much in this particular class. But it's a good definition to keep in mind because other people use that definition. So our goal today is to figure out the first half of how do we figure out what K sub C is. If we want to know anything about what kind of products we're going to get, how much we're going to get versus how much we started with, or what happens if we dump an inert in there, or what happens if we change temperature or pressure, all of that comes down to how those parameters affect K sub C. The path to figuring out K sub C is a little bit obscure. We're going to start with one half of it today, which is the temperature-dependent side, and then we'll talk about the concentration and the pressure-dependent side tomorrow, or not tomorrow, Wednesday. The reason that this is so important is because we are after trying to figure out what is the equilibrium concentration of all of our stuff, right? And that represents the best that you can do. If somebody comes to you and says, should we do this according to such and such a reaction, if you're just trying to figure out if this is a good idea or not, the first place you should start is, what's the best that I can do? Right? The best that you can do is to get to equilibrium. It doesn't matter if you catalyze the reaction or not. You're not going to change what equilibrium is if you use a catalyst. You'll just change how fast you get there. So in order to figure out, am I making enough product to be competitive with somebody else or to make enough money, equilibrium is sort of the benchmark of how far can I take this particular reaction. Is it going to give me the conversion that I want even under the best of conditions? The best of conditions is equilibrium. That's as far as you can get. Equilibrium is usually not 100% conversion. With a few exceptions, like I mentioned earlier, something like combustion, you usually get pretty close to 100% conversion in combustion. So we want to figure out how do we get Kc, because Kc will eventually tell us what's the equilibrium concentration, and that's the best that we can get. In order to do that, like I said, today we're going to start off with one half of that. In order to get to K sub C, we first have to get the more general, what is called K sub EQ, which is the equilibrium constant, no subscript. No, equilibrium constant K sub C is the equilibrium constant in terms of concentrations. The equilibrium constant KEQ is a thermodynamic equilibrium constant. We need to figure out what the relationship is between the two of those. If I could make sparkles appear on this screen, the sparkles would appear around KEQ. This is the best I can do for sparkles. KEQ is the starting point for all of these calculations. By itself, there's one other piece that we're missing that we'll figure out on Wednesday. So by itself, KEQ is not enough to solve these problems. But all of these problems start with KEQ. And it's all based in thermodynamics, and it is only a function of temperature. So KEQ is only a function of temperature. And that's what we're going to focus on today, which is how do I get KEQ for any temperature for any reaction. Once I know that, then we'll see on Wednesday's class how we take that and relate it to K sub C. So it's a somewhat lengthy discussion, and we're starting off with one half of it for today. In order to find KEQ, let's dig up some thermo. I like this part. If we have one species, this is the part, by the way, that your book doesn't do particularly well. So if you want to see an in-depth discussion of this beyond even what I'm going to do here, you'll have to dig up a thermo book. Who remembers the change in Gibbs free energy as being equal to the volume times the change in pressure minus the entropy times the change in temperature? Who didn't get that tattooed on their fingers? I got it. Also recall from thermo that the Gibbs free energy was simply defined as the enthalpy minus the product of the temperature and the entropy. Right, there weren't a lot of different ways. The top equation was originally derived from the first law of thermodynamics. The second equation was nothing other than, turns out that quantity shows up a lot, so it's easy to give it a name, which was G. The last bit of information you need is just a little bit of trickery from our friend the chain rule. Everybody loves the chain rule. If you have the derivative of G over RT, the chain rule says that that's the same as the derivative of the Gibbs free energy over RT minus the Gibbs free energy, that needs to be up on the top, Gibbs free energy over RT squared times the change in temperature. That is not a thermodynamic definition. That's just if G is a function of T and T is T, and we apply the chain rule to that, that's what we end up getting. If we take these and combine them, so we're not doing anything here other than algebra. There's no calculus. There are no other assumptions that we have to make. You probably saw terms like this that would show up in thermo, these partial derivatives that are related to the excess quantities. You probably saw those. I'm just going to keep saying you probably saw those. Don't worry, you don't have to derive any more in here. If we take the partial derivative of G over RT with respect to T and we fix pressure, so almost all of our systems are going to be at fixed pressure, we would find that this is equal to minus the enthalpy over RT squared. Right, we didn't do anything there other than some algebra. There was a little bit of calculus there where we took a partial derivative and fixed the pressure in order to make something go away, but that was about it. So as you guys are writing, you can probably continue this equation vertically, but I'm going to have to go to a next slide. So I'm just going to copy that and move it on to the next slide. All right, so if we take that, here's our equation again. Did that copy okay? Yeah, it copied okay. And we're going to do the following. The long arrow means somebody else did this for you so that you don't have to do it. The first thing we're going to do is multiply this by the stoichiometric coefficient nu sub I. And then the second thing we're going to do is sum for all I. Right, and that's going to give us the following. Minus the total derivative of delta G, circle. Yes, I introduced a circle there. Don't be afraid of a circle. Divided by dt is going to be delta H circle over RT squared. Those deltas, remember I said there's only one kind of delta that we use in this class, which is the difference between products and reactants. So when you see delta H to the circle, or really just delta H, that's the enthalpy of reaction. So when we have delta H, I'm going to keep leaving the circle. I'll get to the circle in a moment. That's the enthalpy of reaction, which you would have learned in 100 as the sum of the stoichiometric coefficients I times the enthalpy of each species. That's the only kind. Every time you see delta of anything, delta is always the sum of the stoichiometric coefficients times whatever that thing is. So here it's enthalpy, so we get H's. So this is the enthalpy of reaction. Apparently that is pronounced enthalpy and not enthalpy. But you wouldn't know that unless I told you, so I'm just going to keep pronouncing it like I'm from Ohio, because, I mean, not to knock you if you're from Ohio, because I'm from Ohio. Same thing with the Gibbs energy of formation, or the Gibbs free energy of formation. It's the sum of the stoichiometric coefficients of all species times the Gibbs energies of each one. So this is the Gibbs energy of the reaction. So what does the little circle mean? Each one of these does actually have a little circle on top of it. So this circle here, and this one down here, that's more like an eye, that circle. The circle means that this is at a standard state. The standard state that we usually use is the ideal gas at 1 bar and whatever the temperature is of the reaction. Right? We can vary the temperature as much as we want. As we'll see, we have to be able to adjust this for some temperature. But the standard state, when we put the little circle on there, means when we want to calculate this, if we want to use those circles, it's for the reaction between ideal gases at 1 bar and at whatever temperature of reaction we happen to have. This, I can't sparkle, but this is the source of a lot of errors. Keep in mind, the way that we are defining this, the way that we get all of our enthalpies of formation and Gibbs energy of formations is all at 1 bar. The units are really important. Depending on what book you go to, their standard state might be 1 bar or 1 ATM. If it's 1 ATM, all the math that we're doing here works, but you have to change your units, which means when you're all done, you're going to have different R's sitting inside there. So the R's that we use, make sure whatever R you're using when you go to do this has units of bar. If you're going to make a calculation that involves pressure, convert the units to bar. Make sure all of your pressures are in bar. That's also a good way to check when you're all done with any algebra that you're doing. Run through your unit conversions and make sure those units either cancel because they were all bar, or whatever the resulting unit is also bar. And that is specific to, I don't want to say this class, it's specific to the source from which we are getting all of our enthalpies and Gibbs free energies. If you go to a NIST web book, theirs are in bar. If you go to one of the library books, which is, it starts with a G, and now I can't remember the rest of it, they use 1 ATM as their standard state. So you just have to be careful where you're getting your data from. Everything that we use will always be bar. KEQ, we've actually already defined, or actually we defined KC. We're now going to define KEQ. We've already written it, we haven't defined it. This term here, delta G over RT, is natural log of KEQ.
Is that a capital K?
Yes, thank you. Let me put the caps on there. Don't forget that negative sign too. There's no way to guess this, right? All this does is make math easier for us. If we never wanted to see the letter KEQ, we'd be fine. All we'd have to do is carry around minus delta G circle over RT. So it's a little easier to write ln of KEQ, and KEQ in general is easier to write than exponential of minus delta G circle over RT. We use KEQ mostly to make our lives easier when we're writing stuff. There's no new definition that we've made here. It's sort of like when we defined over here, the Gibbs free energy is the enthalpy minus T times S. Turns out that's a useful quantity to carry around. People have figured that out over the years. We have also figured out that it's easy to carry around. Natural log KEQ is equal to minus delta G over RT. It's just a helpful thing to carry around. We will see that this becomes our starting point for a lot of our calculations. But in general, if we take this equation and we dump it up inside of our derivative, oh, sorry, one other thing. We don't have to make any changes. Depending on what book you see, KEQ will not be called KEQ. Sometimes it'll just be called K. I don't like just calling it K because we have about 9 Ks to throw around. So I like to be a little bit more specific and give it a subscript. The kind of K that you might have seen in chemistry is Ka. That's the same K that we're dealing with here. I don't know why I said KEQ other than it makes a little more sense because all the problems that we deal with are for equilibrium. So I called it KEQ instead of Ka. But you could see any 3 of those variations depending on what reference you're looking at. I will always call it KEQ, just in case you're digging up. I know you like to go home and read your chemistry books and compare, so you will see that variation if you go see your chemistry books. If we substitute that into our equation, we get natural log, actually the change in the natural log of KEQ with temperature is equal to the enthalpy of reaction over RT squared. This is called the Vant Hoff equation. And we're going to explore a little bit more about what the Vant Hoff equation implies about equilibrium on Friday's class. But at this point, this is the basis of if we could just get a single value of KEQ, we could solve that equation for KEQ at any temperature, right? Because now we know how KEQ changes with temperature. So if we could just figure it out at one temperature, we could integrate that expression and figure it out at any other temperature. And that's the goal of what we're doing in today's lecture in particular is how do I get started? How do I get a KEQ at any temperature? And then how do I adjust it to some new temperature? In order to get KEQ at any temperature, we have to get started somewhere. The way that we get started is to say KEQ, here come 3 more Ks, K0, K1, K2. We're going to calculate 3 separate Ks. The K0 is going to get us close, right? That's going to tell us what would happen to the reaction under standard conditions. K1 is going to adjust for temperature. It's going to get us in the ballpark if we were at a different temperature. K2 is going to say what happens to if the enthalpy term were a little bit different than what we did in K1, which will make more sense when we show it in a moment. So K0, we can get K0 from the definition of what K is. K0 is the exponential of minus delta G circle over RT. Why is that helpful? That is helpful because we can get delta G's at a lot of different temperatures. We can find the Gibbs free energy of various species is tabulated at usually a particular temperature. That temperature is what we would subscript with as a 0. Usually T sub 0 is 298.15 Kelvin. Right? If you just go dig up a book, well, not any book. If you go dig up a book that tabulates the Gibbs free energy of formation of various species or the enthalpy of formation of various species, they're almost all at 298.15 Kelvin. So the reason that this is advantageous is because these values are tabulated. Where are they tabulated? Pick a thermo book, dig in the back, pick your 100 book, it's back there too. I've also given you a spreadsheet that has about 100 of them tabulated that we're going to use, and we're going to see how to use that spreadsheet at the end of class. If you need them, and you need to look them up, go to that spreadsheet, which is eqcalc.xlsx. By the way, last night I tested eqcalc just to make sure that it would work. I uploaded the 97 to 2003 version of Excel. If you don't have Excel, you can download LibreOffice, the open source free version, and it'll work in the Libre version as well. So you don't have to have Excel to use this if you don't want to buy it.
Question?
Yeah.
Does that work in Google Drive too?
That one I haven't tested. If you could test it and let me know. Because I know it doesn't use anything special that I don't think is in Google Sheets, but I think Google Sheets uses a different version of VLOOKUP, and I'm not sure if VLOOKUP will translate, but it might.
Okay.
It might. So K naught is where we get started. That gets us started. It says, what would happen if this reaction occurred under standard conditions, which is 298.15 and 1 bar? How do we make our first adjustment? In order to make our first adjustment, we just integrate the Vant Hoff equation up there at the top. Right now we know one of the K's, we know both temperatures, presumably one of them is 298.15. The other one is whatever temperature happens to be of interest that presumably the reaction is occurring. And we can integrate that equation. If we want to integrate that equation, we could have a problem with delta H circle. Delta H circle is a function of temperature. If to get started we assume that delta H is not a function of temperature, if we assume that it's constant, and we integrate that equation, we will get the following. Oh, that's not supposed to be read. We will get that K sub 1 is equal to K sub 0 times the exponential of minus delta H circle over R times 1 over T minus 1 over T naught. So T naught there again is almost always 298.15 Kelvin. This particular form, though, isn't restricted to using K naught, right? If I give you K at any temperature, you can always use K1, this equation for K1, to adjust that K to another temperature. It just so happens that most of the time when we're using this, the temperature that we're using for T0 is 298.15. But I could give you a K at 400 Kelvin, and you could adjust it to any other temperature by using this equation for K1, because all that does is integrate the Vant Hoff equation, which is fine. But it did make an assumption. The assumption here was that delta H circle was constant. It's still not a bad assumption. So one of the things that you're going to do in your homework is figure out how much that assumption has an effect. So you'll calculate it either with or without that assumption. And you'll see that generally the correction is pretty small. Unless you've got something that has a very complicated form for a heat capacity, then they all tend to work okay. This is also defined as the following, which is what, our fifth K? K sub SC. SC here means shortcut. Why is that a shortcut? Because life is a heck of a lot easier if we assume that delta H is constant. If delta H is not constant, dig yourself up one of these calculators like eqcalc.xls and don't recode all of this because it takes a while to code it in. But it is all just algebra and integrating polynomials. But the KSC is a good place to get started because that correction for a non-constant enthalpy of reaction tends to be fairly small. So if you lack the data that we'll see in a moment that we need in order to calculate K2, which is the full version of KEQ, you can get away with KSC, which is just K1. Actually, now that I look at it, nah, it's okay. It's a little confusing the way that I wrote it there because if you take that K, it's really more like K reference it doesn't have to, like I said before, that temperature doesn't have to be 298. It can be anything that you want. If we wanted to be a little bit more precise, you would do that. Right, what I just did was erase the k naught, because if I were to put k1 is equal to k naught times that exponential and then plug it into the keq, it would look like k naught was squared. K naught's not supposed to be squared. It's just that ksc, aha, see, we're getting it now. You all have erasers, right? So I didn't do anything that you can't do. This is k naught k1. That's a little bit more clear. And by more clear, I mean right. All right, so the k naught gets us close at, or k naught gets us started at 298. K1 will adjust k naught for a constant enthalpy to any other temperature that we want. And if we're good enough with that, if we say, yeah, that's probably going to be close enough for this problem, or we don't have any information to go further, we can just call that the shortcut version of keq, which is called ksc, and that's the product of k naught and k1. Generally, that will get us pretty close. If we want to go all the way to keq and really do things properly, then we also need k2. The reason k2 is kind of a pain in the neck is because, remember, the change in enthalpy is equal to the heat capacity, which is itself a function of temperature, times the change in temperature. Heat capacities are usually of the form A plus B times T plus C times T squared plus D times T cubed. And there's one of those for every species. Right? So you've got, if it's A plus B goes to C plus D, you've got 4 versions of that CP to deal with, which means you have 16 coefficients that you need to carry around, and you need to integrate all of that. Fortunately, that's been done, in the most part, by a lot of spreadsheets that we have. The end result is that K2, which is the final correction that we have, is the exponential of an enthalpy correction term, delta H correction, divided by RT, plus an entropy correction divided by R. What do these look like? The enthalpy correction, these integrals should look somewhat familiar from CENG 100. So that's integrating things like T naught to T of a delta Cp dt. Remember, anytime we see a delta, that's the sum of the stoichiometric coefficients times whatever the thing is. Right, conceptually, yeah, I kind of see where we're going with something like that, in the sense that the CP is going to be a polynomial in terms of T, and we're going to change up all those coefficients because we've got 4 different parameters. So there is a way to evaluate that to get an analytic response so that we don't have to integrate it every single time. And fortunately, that's been done enough that we don't have to reinvent the wheel every time. Then there's a term that looks like an entropy correction that, again, may have showed up in thermo, delta Cp over T times dt. So the idea of K2 is to correct for the enthalpy of reaction as a function of temperature. That's the last correction that we have to make. We can do okay if we assume it's constant, and then we don't have to evaluate these 2 integrals. But if we really want to know what the best estimate for KEQ is, and we're really changing temperatures, if we're not going from just 298 to 400, or we're doing 298 to 2000, and we think that that temperature correction could be important, then we should really use the full version, which includes K2 as an extra correction factor. So just to summarize, we have 2 cases. So KEQ is going to be equal to one of 2 things. In one case, I'll put this one as blue, it's going to be approximately equal to KSC, which is the shortcut, which is K0 times K1. And remember, this assumes that delta H is constant. The other version, if we wanted to be more precise, is to not make that assumption. Actually, there is no squiggle. And now it is just equal to K0, K1, K2. This one, the K0, K1, K2, that's always going to be an EQ calculation. You're never going to have to do that. Well, I'm never going to ask you to do that one by hand. Maybe someday you'll have to. That's always an EQ calc.xls. The blue one is also on there, but you should be familiar enough with it to do it by hand. Right? If I give you the elements of it, you should be able to dump it into that exponential form and figure out K at any temperature given another K, or if I give you all of the enthalpies and Gibbs free energies of formation, you should be able to get KSC by hand. That's why it's called shortcut, because you don't have to evaluate any nasty looking integrals or anything like that. And so I will ask you in your, I think it's the very first, yeah, it's like problem 2.1 and 2.2. 2.1 is use EQ calc to get a bunch of these values, and 2.2 is test yourself and make sure you can get all those using KSC. That should be really good practice because KSC is the only one that I would ever ask you to calculate on an exam. So let's see an example of how do we use this EQ calc spreadsheet. So let's take as our example system carbon monoxide plus 2 hydrogen in a reversible reaction to form methanol. And we're going to set this at 400 K. So we want to try to figure out what is KEQ at 400 K. These, by the way, are all gases. There are liquid forms that we're going to look at eventually, but just for this example, we're going to figure out what is the equilibrium constant KEQ for the formation of methanol from carbon monoxide and hydrogen. In order to do that, I'm going to pull up the EQ calc sheet so that you can see it. Unfortunately, if you're paying attention to the podcast, I'm going to stop it now.